PV equals nRT. This is a popular equation in chemistry. The pressure, volume, and temperature are the variables that we're considering here. N we'll find will be constant. R is the universal gas constant. So pressure, volume, or temperature are the three variables. But notice, it's a straight multiplication across. So I mean, it's the anything we divide or multiply by, we don't need to add or subtract to. So if we remember this form of it, PV equals nRT, we can go through algebra and solve for any of these. So a good exercise to solve for is R. We'll find what the value of R is at any given pressure, volume, and temperature. So for example, first thing we could do, there's numerous things we can, is we'll divide to isolate R by itself. So we'll need to divide both sides of the equation by N and both sides by T. So let's start here with PV equals nRT. We'll divide both sides by N over T. Put a little thing in there. Divide this side by NT. Well, let's see, this is the fun part. We get to cancel out. N's cancel, T's cancel to 1, up to 0. So all we're left with here is R equals the pressure over the volume over N, which is sometimes known as grams per mole, and the temperature. Then when we put the values in for any given pressure, volume, mole, which a lot of times is 1, so we can even think of this as 1 PV over T. This is where the units come in. This is where everybody gets scared. So we're going to start with the metric system first before we deal with the units of this equation. But by the time we reach this stage, we'll have it down. The metric system. It's all on the base 10. And base 10 means just moving the decimal point. So counting in metric is easy. The first dimension that we measure is the length. So we have the meter versus the yard. We'll come to like the meter best. In order to understand the metric system, since we're dealing with exponents, which are powers of 10, there's a shorthand notation we call the scientific notation. What this does is most commonly puts one digit with a decimal point, and usually only 3 significant digits, we'll call it. So say like 4.23. If we measured 4.2366, we only need 3 significant digits here. Decimal place here. So if we had this times, say, 10 to the minus 6th power. Again, we know what that means is that this decimal place has been moved 6 places to the right of 0. So this really could be written as 0 point, and what we would have to do now is, it gets confusing, but work with this to get it. To move the decimal place back to get this to be 10 to the 1. So we need to move it 6 places this way. It should be like 1, 2, 3, 4. It gets hard, so what we'll do is we've got to draw the zeros in. So let's do this again. We'll draw a bunch of zeros and then 4.23, and that is 10 times -6. So now what we can do, if we see this, is move it 6 places. 1, 2, 3, 4, 5, 6 places. So what the number then would be 0.1234542 This is what the real number is. So if we were measuring this, we would measure 0.0000000. We don't want to deal with all these zeros because there's more of a chance of making an error. So what we find we can do is write it in what's called scientific exponential notation. Scientific usually means that there's 3 digits and a decimal point here. Exponents being powers of 10. The next thing we do in science is have representations. So say this is this number of grams. Well, if we move this decimal place, say to the negative side, 1, 2, 3 places. Now instead of writing that all out, we would write 0.00423. And since we moved that 3 to the minus side, it could now be times 10 to the minus 3 grams. But in order to avoid writing 10 to the minus 3, if we look on the table, we see the scientific notation exponent symbols. This is what milli is used to represent. A 10 to the minus 3 places. So this number written this way is milligrams. Well, we can go another 3. 1, 2, 3. And this would be 10 to the minus 3, another minus 3. This would now give us 4.23 times 10 to the minus 6. That's where we started with. Instead of writing this as times 10 to the minus 6 grams, we look at the next exponent, minus 3 for milli. Another minus 3 is mu, called micrograms. So an easier way to write this is 4.23 micrograms. So if we see this, we need to be able to work backwards with the exponent. That's why it's so important to write these zeros in and count it, like going back to kindergarten. Move it, draw your arrows, and you'll never make the mistake. Okay, a conversion problem would be converting from, say, a unit of meters, we'll say millimeters, to American, which would be feet, inches, yards. So one conversion we would need from metric to English. And if we memorize this one, it's maybe the only one we ever need. 25.4 millimeters equals 1 inch. Okay? We got meters and we got inches. This is the conversion. Everything else is kind of known, hopefully. We know there's 12 inches in a foot. We know there's 3 feet in a yard, 36 inches in a yard. Well, meters is where we're kind of new to, so we get all confused and baffled, but we don't need to because we have everything we need. So let's convert. Say we want to know how many meters, or how much of a meter, or how much of a yard is in a meter, vice versa. Well, if we know 1 inch equals 25 millimeters, the question would be how many 36 inches meters? The milli of, that's simply just 10 to the minus 3 meters. So what did we do? We took 36 times that, so 36 times this. That's the conversion. That's all there is to it. If you have a calculator, calculate